This video is brought to you by mywayteaching.com.
In this part, we are going to study Maxwell distribution function. Okay, in a given mass of gas, the velocities of all the molecules are not the same, isn't it? If we consider you know a group of gas molecules, the velocity of each one of that molecule will be different. Even when the bulk parameters like pressure, volume, and temperature are fixed, the velocities will differ. Collisions change the direction and even the speed of molecules. However, in a state of equilibrium, the distribution of speeds is constant, or we can say the distribution of speed is fixed only in case of equilibrium. In other case, the velocity will differ for each of the molecule. See, these distributions are very important and even they are very useful when dealing with systems containing large number of objects. You just consider as an example ages of different persons in a city. Okay. Okay, ages of different persons in a city. See, it is not feasible to deal with the age of each individual. So we can divide the people into groups, means like children up to age 20 years, and then we can divide it as adults from 20, between 20 and 60, and we can say old people above 60, isn't it? So if you want more detailed information, we can choose smaller intervals like 0 to 1, 1 to 2, 99 to 100. So we can choose intervals of age groups. When the size of the interval becomes smaller, say half year, the number of persons in the interval will also reduce. So roughly half the original number in 1 year interval. So the number of persons which are, we can represent it with the d of n of x in the age interval x, and x plus dx is proportional to dx, that is equal to nx into dx. So here we have used nx to denote the number of persons at the value x. Okay, this is one simple example. If you consider another example, that is molecular speed distribution, it gives the number of molecules between these speeds, that is v and v plus dv. So here we can write d of n of v is equal to 4p n a cube e raised to minus bv square v square dv, that is equal to NV into dV. So this is called Maxwell distribution. The plot of NV against V, you can see in this particular figure. The fraction of the molecules with the speeds v and with speeds v plus dv is equal to the area of the strip. You can see here this one. So the average of any quantity like v square, it is defined by the integral 1 by n v square dn of v, which is equal to square root of 3 kbt by m, which agrees with the result which is derived from more elementary considerations. This is the Maxwell distribution function. Okay. Now let us see one simple problem. Uranium has two isotopes of masses 235 and 238 units. If both are present in uranium hexafluoride gas, which would have the larger average speed? If atomic mass of fluorine is 19 units, estimate the percentage difference in speeds at any temperature. So here we should estimate the percentage difference in speeds at any temperature. Let us find the solution for this. See, at a fixed temperature, the average energy is constant. So smaller the mass of the molecule, faster will be the speed, and the ratio of speeds is inversely proportional to square root of the ratio of masses. So the masses are 349 and 352 units. So here we can write 352 by 349 whole raised to 1 by 2 will give 1.004. So here we can calculate the percentage difference in the speeds as delta V by V, that is 0.44%. Okay. See, uranium 235 is the isotope needed for nuclear fission. We use this uranium 235 in nuclear fission. And uranium, to separate it from more abundant isotope, that is uranium 238, the mixture is surrounded by a porous cylinder. The porous cylinder must be thick and even it should be narrow so that the molecule wanders through individually, colliding with the walls of the long pore. You can see in this figure molecules going through that porous wall. The faster molecule will leak out more than the slower one, and so there is more of the lighter molecule outside the porous cylinder. So the method is not very efficient and it has to be repeated several times for sufficient enrichment. When gases diffuse, their rate of diffusion is inversely proportional to square root of the masses, isn't it? So here through this porous wall, the molecules will flow. Now let us see one more important example. When a molecule hits a wall, it rebounds with the same speed. When a ball hits a massive bat held firmly, the same thing happens. Again, it rebounds, isn't it? However, when the bat is moving towards the ball rebounds with a different speed. Does the ball move faster or slower? Okay, here when bat is moving towards the ball rebounds with a different speed. So whether that ball move faster or slower, that is the first part. Second question is, when a gas in a cylinder is compressed by pushing a piston, its temperature rises. Guess at an explanation of this in terms of kinetic theory using this first one. Okay. The third one is, what happens when a compressed gas pushes a piston out and expands? What would you observe? Sachin Tendulkar uses a heavy cricket bat while playing. Does it help him in any way? So these are all the application level questions. So coming to the first part of the question, that is when a molecule hits a wall, it rebounds with the same speed. Whether in case of a ball, when it hits a bat, when bat is moving towards that ball it rebounds with different speed. Whether that ball is moving faster or slower. See, let us consider the speed of the ball as u. Relative to wicket behind the bat. If the bat is moving towards the ball with a speed v, okay, if the bat is moving towards the ball with the speed v relative to the wicket, then the relative speed of the ball to bat is given by what? Isn't it? That is v plus u towards the bat. Again, when that ball rebounds after hitting that bat, its speed relative to bat, that is v plus mu, is moving away from the bat. So, relative to the wicket, the speed of that rebounding ball will become v plus mu. That will be equal to 2v plus u, isn't it? Which is moving away from the wicket. So here the ball speeds up after collision with the bat, isn't it? So the rebound speed will be less than u if the bat is not massive. For a molecule, this would imply an increase in temperature. Okay. So for the remaining questions, you can compare this cylinder to the wicket, and for molecule to the ball, you will get the solution for all those things. Okay.